Thanks, Greg. So my name is Paul Nagy, along with Chan Yu, who is my co-lead for medical imaging. We have a medical imaging working group, which started about 3 months ago. We meet every 2 weeks. We alternate between 7 a.m. and 7 p.m. to facilitate our each parts of the globe. And we found it's been great to having conversations on both of them. We have a message for you, and that is, if you like EMR data, you are going to love images. Images have the best data when it comes to looking at the progression of disease, when it comes to looking at the organ levels. And so if you haven't been following the medical imaging field, I'm going to give you just a quick primer of what's been going on the past 10 years. There's been a bit of a revolution that's been going on called deep learning imaging. And what's happened was there was a competition on the web every year where they had 1 million photos, and all the computer scientists would get together and try to predict algorithms that would classify them correctly. And what happened was in 2012, they came out with something called a deep convolutional neural network, and it radically outperformed the rest of the field and started giving rise to this field of deep learning for imaging applications. And this has really been driven by a lot of major companies like Google and Facebook. This is why we now have things that do facial recognition, self-driving cars. All of this is built on these types of algorithms that are able to then take the contiguous natures of pixels and combine them to create complex features. And so architecture, typically what they do is we do like a whole slew of different edge filters and different combinations. We stack them together and it gets complex shapes. And then we plug it into a neural network, which is a bit of a universal fitting function. And voila, not only can we do classification, we've seen also the ability to do segmentation around organs, around tumors, getting us morphology. And so we've seen a large increase in the number of publications on PubMed in imaging applications looking to do things. We've seen FDA approval of deep learning applications. We even seen one of my favorites is one for stroke. So within minutes of having a CT scan, we have a stroke detector, which will flag a radiologist and say, you should look at this patient right now, so that within 60 minutes, we can get them on the table. And so we're now seeing deep learning algorithms coming based, and this can create a new level of information for progression of disease. We are even seeing new journals coming out dedicated to convolutional deep learning networks. And so this is really a big area, and we want to be able to tap all these great phenotypes, all these incredible biomarkers that help us understand the progression of disease and plug them into the OMOP model. And so to do that, what we're doing and so we've been meeting for the past few months. We've got great groups from Stanford and Toronto and from European partners. And what we've been able to do is try to put together what our main goals are. The first is there's a lot of imaging research going on, and we want to be able to conduct imaging research based in Atlas, based on the robust way that we create cohorts in a reproducible way. And so our first goal is to take, basically, if you look at medical imaging, there's a standard that's been around since 1993 called DICOM, Digital Imaging Communications in Medicine. And that DICOM standard is actually a very rich standard. It's much better than HL7 version 2. It actually will tell you a lot about the imaging, how it was acquired, what the field of view was, what the slice thickness was, what the energy or the current and the voltage. And so basically you get a lot of acquisition parameters. And those are really useful for us when we're trying to create a data set and trying to study an algorithm. We search for, give me all the chest CTs of patients who had a certain protocol, or give me all the abdominal CTs or MRs. And so we often are searching by modality, by body part, and by protocol. So those need to be amenable within the OMOP model. So our first recommendation for an extension is having a imaging study table where basically every DICOM study can have some of its important acquisition parameters elevated so that we can search for them for doing cohort discovery, like modality, laterality, contrast, technique. And what's interesting here is with medical imaging, DICOM has really moved quite a bit in the past 20 years, and they are now all web-based like REST and FHIR. And so you can even link to the actual image data set right from within a URI now. And so we can actually have an imaging study. This would obviously, in our mind, this would link to a procedure occurrence. So right now we have imaging studies in OMOP. We know that they occurred because we'll see them in a procedure occurrence as a CPT code or an ICD-10 PCS code or a SNOMED. So what we have is we are able to then link a procedure occurrence to an imaging study, and then we get a lot more about the actual acquisition around that study. And the RSNA and the ACR has done a lot of work with us, combining or done a lot of work working on bringing a lot of the data elements from DICOM from the field of radiology into LOINC. And this is called RADLEX, and there's capabilities for how we do ordering playbooks for standardizing our imaging procedures and for defining measurements within radiology that we then can transmit into LOINC. And once it's in LOINC, we get it as part of our LOINC terminology. So this is just the first side. It's just being able to say, whenever we have, people might not know, but radiology and imaging was digital well before the hospital was. So hospitals really didn't go digital until about 10 years ago, where radiology has been digital for about 20 years. So we have often hospitals will have great PACS systems or a vendor neutral archive where they have a host of DICOM studies in them. And so we want to be able to plug into those archives, be able to pull data out of that, and then populate our OMOP data set based upon those studies to be able to then pull those features into help our researchers discover what images are available. Okay, so that's our first goal, is just to support imaging research. Our second goal is really, I think the really important goal is to bring features derived from medical images. Now that we can do really powerful segmentation algorithms off of medical images, how can we bring them into the OMOP model? Basically, we want to get them into the measurements table and the observations table. When we do a mammogram and we see a ground glass nodule, when we see a certain size of a tumor, we want to be able to have all those measurements going into our measurements and observations. But we also want to maintain provenance. And so we've been learning from the NOTE NLP group, from the genomics group, and from the telemetry waveform group about how do we make sure that we maintain provenance while we do that. And so basically what you'll see here is, in addition to an imaging study, which is at the time of acquisition what we know about the imaging, an imaging feature will be something that's extracted by a human or an algorithm, and it could be like a rhesus criteria, which is the long axis size of a lung nodule, say it's 1.5 centimeters, and we have an algorithm that derived it. And that imaging, that basically that feature will then end up in the measurements table as a rhesus criteria, but we want to know how we derived it, what images it came from, and basically the algorithm that was around it, so that we can actually study it as these algorithms get better calibrated, and we're actually trying to evaluate the algorithms, not just the data that's coming off of them. So this is an important part where we have a second extension where we have a table where we're going to take all of our features and have the provenance that goes into measurements and tracks where they go into, just like NOTE NLP has a domain concept ID saying this feature ended up in measurement, and here's its ID. We want to be able to maintain that, track that back. We would like to get this to the point where we can actually reconstruct an algorithm. So we can rerun an algorithm. It knows what DICOM images it came from. We can have the algorithm system know enough about itself to know the parameters it chose and to be able to rerun it as a pipeline to see if we get the same measurements and observations. And this is a way that we start testing our algorithms. I think one of the big challenges with deep learning and medical imaging is it is very much a black box, and it is very prone to out-of-band error and overtraining. And so being able to study the algorithm itself is going to be very important for deep learning to gain relevance and traction in improving our ability to study healthcare. So these are our two main goals: is having an extension that the CDM group is happy with, that is a nice, simple model that we can extend for waveform and genomics, and be able to then plug in all of the images we get from radiology and cardiology and dermatology and all the other imaging ologies, but also be able to extract features from those images and be able to bring them into the OMOP data model. So those are our first two goals. And our third goal is actually, you have to try it out to see if it works. And so our third goal is to create reference implementations of this infrastructure and to see what works and what doesn't work. And so what's great about medical imaging, there's also a very robust open source community in medical imaging. There's the XNet, which is a great research community around DICOM imaging research pipelines. And there's MONAI, which is a great community that has built a medical imaging wrapper around PyTorch, which is one of the predominant convolutional neural network algorithms that are used by some of that plugs right into your GPU hardware. And so we feel that there's a strong ecosystem for us to plug into. We'd like to demonstrate these reference implementations, and Chan and I have a friendly wager of who's going to get there first with our institutions. So our formal OKRs are, one is we're going to incorporate a data model and give it to the CDM, and they're going to approve it. So hopefully we'll identify the data elements, the necessary to accomplish these goals, the use cases, the vocabulary, the schema, and doing it in a way that is fairly similar to how we do genomics and telemetry, and somewhat similar to NLP. They have a very unique problems to solve. And then in addition to that, we would like to have reference implementations to be able to see what use cases we're able to solve, what challenges it presents, what opportunities we might want to grow with it, but basically building off of existing imaging, open source imaging architecture. So our goal is to write a couple papers and to demonstrate a reference implementation for how you can take images and be able to create this. So we have, as part of any good data model, we have use cases that we're trying to highlight that are typical in the imaging world. And this is a typical one where we like to study lung nodules, pulmonary nodules, and look at their doubling rate and how they develop over time. So a lot of imaging studies are looking at temporal progression. So this is a typical one for lung cancer that we have. We have another one for breast cancer and for pre and post operative imaging analysis. And so these are three big domains of research that are being conducted today. As a matter of fact, mammography CAD work was actually being done in the late 80s to early 90s. Some of the earliest CAD work in healthcare was in mammography. So it's kind of exciting to bring in those use cases for all the screening that we do. So that's our imaging update. We encourage you to join us. Again, we meet on 7 a.m. and 7 p.m. on Wednesdays about twice a month, and come and see what you can get out of medical images.